Good morning, everyone. So I'm Dilani from Ghent University, Belgium, and I'm the ESR 13 of this GreenCarbon project. And today I'm going to talk about the biochar from greenhouse waste and its characterization and the evaluation for its potential to use in horticultural growing media. First, I'm starting with the use of peat moss in horticultural growing media. Peat moss is the dark brown fibrous product of a sphagnum moss and the other organic material that decompose in peat bogs over thousands of years. And this material is heavily used in horticultural growing mediums because of the number of benefits. Peat is clean and sterile, and it has a very high moisture retention capacity, and it has a comparatively uniform composition. And there are some downsides too. Peat is very low in nutrient and it has a very acidic pH, and extraction of peat is not non-renewable. So in this table you can see some of the properties of the sphagnum peat and the properties of the other existing growing medium constituents. And as I mentioned before, the extraction of peat is not sustainable because 3% of Earth land surface area are covered with peatlands, and these peatlands contain the 1/3 of world soil carbon. And this system are very fragile to disturbances because of the peat extraction for the horticultural purposes. The current carbon dioxide emissions over 600 million tons per year. So, as a sustainable approach for the peat replacement, in recent literature, biochar gaining attention as a growing medium constituent. So, when considered about the biochar properties, it has a greater bulk density than the peat, perlite, and vermiculite, and it can be manufactured in different particle sizes. And biochar has a high specific surface area, cation exchange capacity, and a comparatively high pH and electrical conductivity. Also, biochar is black in color, which can be favorable for the root growth aspects. However, all these physicochemical properties are based on the feedstock composition and the pyrolysis production conditions, as you can see in here. Even for the same biochar, under different pyrolysis production conditions, its properties can be changed, and also for the same production conditions with the different types of feedstock material, it can be changed. So in my experiments, I use a spent growing medium as a feedstock material, both the spent growing medium alone and the spent growing medium with the plastic wrap around it as a feedstock material. So we carried out pyrolysis experiments using this growing media and the growing medium with the plastic grow bags at 350, 450, and 550, and we produced 6 types of biochar with and without plastic incorporation in the feedstock material. So in here you can see the pyrolysis product yields. So as expected, with the increase of the pyrolysis production temperature, char content decreased and the more oil and gas were reported, and there were no significant event of plastic in the feedstock on the biochar yield, but there was effect on the liquid and gas production. The condensate amount is increased and the gas content decreased with the addition of this small level of plastic content. And then in here you can see the potentially toxic element concentration of the produced biochar types and the phytotoxicity of the biochar samples. So we assessed the phytotoxicity in terms of the cress seed germination, and we did not observe any significant difference between the different biochar types for the cress seeds germination. And in terms of the potentially toxic element concentrations, for all the biochar types, they were within the IBA thresholds. And for the, yes, as I mentioned before, I produced 2 types of biochar. BC is the biochar without a plastic in the feedstock material, and the BCP is the biochar produced with the plastic in the feedstock material. So as you can see in here, in 3 different temperatures, with the increase of pyrolysis temperature, the polyaromatic hydrocarbon content get reduced, and both biochar produced at 450 and 550 had the lowest polyaromatic hydrocarbon content compared to the biochar produced at 350, and this biochar, the 450 and 550, had the polyaromatic hydrocarbon content below the thresholds imposed by the European Biochar certificate. So depending on all these aspects, we decided to produce Biochar in 550 in scale-up production. So in here you can see that we produce another two types of biochar using the stage 3 reactor in the UKBRC and the BC and the BCP with and without plastic in the feedstock. And then we assess the evaluate the possibility of the using of this biochar in horticultural growing media. In here you can see the chemical characterization results of the BC and the BCP, and here the basic characterization results, and here the nutrient contents and the potential toxic elements and the other contaminants. And compared to the when consider about the contaminant levels, most of the potential toxic elements were within the IBA limits, and also within the limits for the polyaromatic hydrocarbon content and the total toxic equivalency concentration. And other than that, the BC, the biochar produced without plastic incorporation, had high ash content, pH, EC, and nutrient content. And the other type of biochar had the high carbon and hydrogen content, maybe because of the addition of plastic into the feedstock. Yeah. And then we formulated 7 substrate formulations using this BC and BCP biochars. So for the control, we keep the P10 perlite in the 70 to 30% volume basis, and we kept the perlite content constant throughout the growing medium formulations, and replaced the peat by 23, 35, and 47 percentages. And consider about the particle size distribution. Particles less than 0.25 millimeter increase with the biochar content, and the particle over 2 millimeter particles decrease with biochar content, and particles in the range of 0.25 to 2 millimeter and was increased with the biochar content. Then the physicochemical properties of the formulated substrate, and pH, EC, and the dry bulk density increase with the biochar content, and the airfield porosity and the boat holding capacity reduced with the biochar content, and we did not observe any phytotoxicity in terms of the germination rate. So in this table, you can see the values for the physicochemical properties and the pH and EC, and here you can see the optimum range. So for the water holding capacity, except the control, none of the biochar containing the mediums did not have it in the optimum range, and the airfield porosity also only in the control and the 23% of biochar added treatment. And for the total porosity, all biochars within the range, and pH, it's also only within the control. And for the EC, except the PC47 added treatment, other treatments had the within the optimum range. And we did not observe any phytotoxicity in these growing medium formulations in terms of the crested germination. And we did a plant growth experiment using marigold, and as you can see in the left, you can see the flower growth in different substrate formulations, and in the right you can see the root growth in different substrate formulations. And in here with the control versus BC23, control versus BC34 likewise. So in here I have listed some of the key plant growth parameters: the number of flowers, weight of flowers, and the shoot and root weights. So according to the results, up to 47% biochar did not show any significant difference compared to control in terms of the number of flowers and the weight of flowers. Also, when considered about the number of flowers and the weight of flowers, there were not significant difference between the PC and BCP in each biochar ratios. So with this, I would like to conclude that we investigated the plastic level as a plastic wrap. It's a plastic bag up to 2.5%, which is made of low density polyethylene in the feedstock. And we selected the pyrolysis process conditions in 550, and it could produce biochar with less contaminants than the threshold imposed by IBA. And also both these BC and the BCP biochars can be used to replace peat up to 35% without compromising marigold flower growth. So therefore, we spent growing medium waste alone, and together with waste grow bags under this investigated plastic level, of course, can be used as a feedstock to produce biochar, and that biochar can be effectively used for replacing peat in horticultural growing media without imposing any adverse impact on the plant growth. So I would like to acknowledge the financial support given by the GreenCarbon project and also the academic and industrial partners of this project. Thank you very much.
Thank you, Dilani, for a nice presentation. So we are open for questions. The first one from Gianluca. How did you quantify the pH content?
Wait, I cannot see the screen. Can you repeat the question, Christian?
How did you quantify the pH content?
Yeah, it's with the method described in the European Biochar certificate methodology, and which is associated with the 24 hours of extraction with toluene, and followed by the GCMS quantification. Yeah.
And second question from Sylvia.
Yeah.
Did you measure how the carbon percentage changed with pyrolysis temperature, the carbon content?
Yes. I think, yeah, in this table, I only present the fixed carbon content, but I did not present the total carbon content in this presentation. With the increase of the pyrolysis temperature, there was an increase of the total carbon content. Also, yeah.
And the last question from myself. So how did you choose the 2.5% waste plastic edition? So why 2.5%?
Yeah, the growing medium we use initially contained 2.5% of plastic, as it's around wrap. So that's why we kept the original plastic ratio as it is.
Okay. Thank you very much, Dilani.